Okay. Okay, hi friends. So this lecture today is going to be about what we expect to happen and how we expect the climate to change in the 21st century. So obviously we're 20 years into the 21st century, so it'll be sort of a recap of the observations, and I know we've already had that lecture in class, a recap of the observations that we saw in the 20th century and the beginning of the 21st century, and then what we expect to see going forward. So a forecast for the future. And lucky for you all, my class, I'm also broadcasting this lecture live, and it will be saved to my social media so that if anybody wants to see it and get really depressed about climate change, then it'll be there forever. All right. So my ugly face is in the way here, but we're going to start with, we're going to talk about these things called SSPs, shared socioeconomic pathways. These are sort of baseline socioeconomic scenarios of sort of what we expect the next 80 to 100 years to look like, not in terms of climate change and climate change policies, but just in terms of how we expect our socioeconomic world to progress, to look. And so there are groups of sort of social scientists and physical scientists and economists who put together 5 SSPs, 5 shared socioeconomic pathways, which are sort of the scenarios that will guide what we think is going to happen in terms of climate change going into the future, right? Because we can't know what's going to happen. So we have to model it. We have to use everything that we know about our world, our economics, our physical climate, and people, and what we, and then sort of make a best guess on like what we think will happen in the future. And if we were meeting together in class, in person, then our next class would be taking each of these 5 scenarios, breaking into small groups, and kind of sort of using our creativity to envision what a future world looks like under each of those SSPs. So in lieu of that, we're going to hopefully try and do this group activity through Slack, but we'll see how that goes. So anyway, there are 5 SSPs, and I will show you what the text of those are on the next slide, but the text is kind of long, so I don't expect you to read it or know it all just from this sort of simple lecture. But they basically go from a very sustainable world to a really unsustainable world with a lot of nationalism, rigid boundaries, wealth disparities, etc., etc. So SSP1 is kind of the sustainable scenario, and then SSP3 is like the hyper nationalist, lots of borders, lots of all the things that sort of Donald Trump kind of embodies, but globally and like times 100. And then SSP4 and SSP5 are kind of mixtures of green and really nationalist, sort of hyper-capitalist policies. SSP2 has the incredibly creative name of being the middle-of-the-road scenario, where everything is just kind of the same as it is now. So these 4 plots here show what the projections of each of these variables are for population and education, for example, for urbanization, for GDP, gross domestic product, and then for GDP and Gini coefficient, which is a measure of wealth and income disparity. And so you can see each of the scenarios, 1, 2, 3, 4, and 5, by the colors. So SSP1, which is kind of the sustainable scenario, is shown with the green. SSP3, which is kind of what I'm going to consider sort of the worst case scenario is shown in the red, and then everything else in between. So you can see in terms of sort of population, in the green scenario, population, in the SSP1 scenario, in the green scenario, we can call it the green scenario, population kind of peaks in 2060 and then declines a bit by 2100. And then in SSP3, sort of the worst case scenario, population continues to rise through the end of the century. And then in terms of literacy rates, the highest literacy rates are in SSP1 and SSP2, and then the lowest literacy rates are in SSP3 and SSP4, and you can kind of see that here and here. Urbanization, SSP1 envisions a very urbanized world, people concentrating in cities. This is, of course, generally viewed as kind of a better delivery of resources. Whereas SSP3, which is the hyper-nationalist scenario, it has much less urbanization, so people kind of siloed in their suburban lawn with their fence around it and maybe their security system, and then their community is gated, right? So that's the sort of worst case scenario. You can see, interestingly enough, that in the hyper-nationalist case, that scenario, that SSP, has the lowest GDP at the end of the century. The sort of sustainable scenario has kind of a middle-of-the-road situation, and then SSP5, the highest. And then in terms of wealth and income disparity, you can see that sort of the green, the sustainable SSP1 scenario has the lowest Gini index, so the lowest wealth and income disparity, whereas the worst case scenario 3 and then the bad case scenario 4 have relatively high income and wealth disparities. Okay, so here are those scenarios. I'm not going to spend a lot of time going through them right now, but I will post these to the Slack so that you all can have access to them, and so that we can do our group work together. But SSP1, as I mentioned, is the sustainability scenario, taking the green road. So you have the world shifting to like a more sustainable path, respecting environmental boundaries over necessarily political or economic ones. It's driven by an increasing commitment to achieving development goals. Inequality is reduced. And then consumption, which is a big component of this, is oriented towards low material growth, lower resource energy intensity, so overall less sort of consumerism. SSP2 is the middle of the road, where it's sort of like basically what's happening now, what the sort of path we're on now, with very little sort of political or economic changes. SSP3, as I mentioned, is what I consider the worst case scenario. So the rocky road, right? Resurgent nationalism, concerns about competitiveness and security, kind of everything that sort of was embodied, honestly, by the Trump campaign and sort of Trumpism, if you will. So countries are becoming increasingly more isolated, and regional needs are prioritized over global collective needs, etc. And you'll also notice that next to these SSPs, it says things like high challenges to mitigation and adaptation, or low challenges to mitigation. So these SSP scenarios are not considering any climate change policy. These are just what the socioeconomic world could look like in 100 years. And so the SSP3 world would be a world where it would have what they call high challenges to mitigation and adaptation, which means that in that world, it would be very difficult to mitigate or stop climate change and adapt to climate change. So if we were to allow climate change to continue to progress, in the SSP3 socioeconomic scenario, it would be very difficult to adapt to that world, in addition to being very difficult to mitigate that warming or sort of slow down climate change. SSP4 and SSP5 kind of take a slight sort of bent on SSP3. So SSP4 is kind of a world that's defined by inequality, where perhaps there would be low challenges to mitigating climate change, right, to stopping climate warming, but there would be high challenges in this world to adapting to climate change, and presumably that's because there would be deeply bad stratification between sort of the wealthy and the less wealthy, the global north and the global south, right? That sort of thing. And then in SSP 5, that's a fossil fuel development world. That's a world where the markets are really competitive, and we continue down this path of exploitation of fossil fuels and resources. And so there would be very high challenges to mitigation in this world, but presumably in SSP 5, there would be great advances in engineering. And so perhaps low challenges to adaptation. We could engineer our way out of climate change, although you all know that I'm very skeptical that engineering is going to be the solution to climate change. Okay, so here's the point in the class where I would ask you if there are any questions on these, but since I'm talking to my computer, I can't do that right now. Okay, so these are what certain aspects of the climate and Earth system look like under these scenarios, assuming that there is no deliberate mitigation of climate change, right? So these are just, if these scenarios were to play out as they've been written, with no specific policies aimed towards mitigating or curbing climate change. So for example, if we look at cropland, in the sustainable SSP1 green scenario, you see that the amount of land allocated towards crops, allocated to growing crops, doesn't really change that much from now-ish to the end of the century. But in SSP3, the worst case scenario, or the sort of high challenges to mitigation and adaptation scenario, you see that by the end of the century, there are about 800 million hectares more cropland allocated across the globe. So presumably more conversion of forest. And so you can see that that tracks really well with the forest variable, where you can see that sort of in the high SSP3 worst case scenario, the number of hectares, the amount of land that is considered forested across the globe, would decrease very substantially by about 600 million hectares, probably about the increase in cropland. Okay, but in SSP1, for example, the amount of forested land across the planet would increase pretty significantly, 3 million hectares. Pasture follows kind of a similar trajectory with cropland, and other natural lands also follow a similar trajectory with forested land. Okay, looking at sort of and remember, keep in mind, this is just the SSP scenarios without the climate change policies on top. This is just what the world could look like in 2100 socioeconomically, not considering any mitigation of climate change. So in each of the scenarios, this is what the allocation of primary energy sources would be by 2100. So you can see currently we're using, our energy usage is dominated by, of course, fossil fuels, by coal, oil, gas, coal, oil, and gas, right? So this is gas, the orange is gas, the red is oil, and the gray is coal. And then very little of our energy is derived from renewable sources. In the SSP1 scenario, in the sustainable scenario, as you might imagine, the amount of energy that's sourced from renewables is significantly higher. And all of these down here are just different economic models that are used to model these things. So you can see that the usage of coal stays about the same, flat, and perhaps the usage of oil decreases slightly, and the usage of natural gas increases slightly, but biomass and renewables increase significantly. In fact, in all of these scenarios, biomass and renewables do increase rather significantly, except, I would argue, in the SSP3, which again is the worst case scenario pathway, where renewables do increase significantly over sort of what they are now, but not as much as, for example, coal usage, oil, and natural gas, right? So you can see in SSP5, for example, sorry, I'm like kind of off the screen now. In SSP5, for example, the amount of oil and natural gas usage increases very substantially, and very little attention is paid towards conversion to renewables. Okay, so here is what would happen to our emissions of various greenhouse gases, and we talked about greenhouse gases in class. So this is what would happen in each of these SSP scenarios to our emissions of greenhouse gases and also of air pollutants, assuming, again, no climate change mitigation policies are instituted. So this is just like what would happen in the scenario. So you can see if we do follow the sustainability scenario, then our amount of carbon dioxide output would stay flat or decrease slightly. This is with no policy, just with this economic trajectory. And then, of course, in the SSP3, again, the red, emissions increase rather significantly. And then in SSP5, which is the fossil fuel heavy scenario, our greenhouse gas emissions increase astronomically, actually. Same with methane, CH4 is methane, right? And then N2O, that's nitrous oxide, also a greenhouse gas, which is derived from the tailpipes of cars and also from fertilizer. Okay, but in terms of our air pollutants, even in sort of the worst case SSP3 scenario, air pollutants would decline a bit, assuming no climate change mitigation policies again. So, but of course, in the best case sort of sustainability scenario, air pollutants would decrease rather significantly, and that's because of the emphasis on conversion to renewable sources of energy. The last panel here, radiative forcing. I know we talked about the radiation budget in class. The radiation budget, right, is a measure of how much incoming energy from the sun, how much incoming radiation from the sun, how much the difference between that and how much energy is outgoing, emitted by the Earth. We want that, of course, to be zero. We want incoming minus outgoing to be zero. The reason we have global warming, the reason we have climate change is because incoming minus outgoing is not zero, it's actually positive, which means that there's an accumulation of energy in the climate system. And as of 2020, we've accumulated about 2.5 or so watts per meter squared of excess energy in the climate system. That's why we are seeing warming, because we've accumulated this extra energy over the last 200 years. So assuming we institute no policies to curb climate change, in the SSP1 scenario, for example, the amount of energy, of radiation, of we call radiative forcing, that is increased by the end of 2100, by the end of the 21st century, we would have accumulated about 4 to 5 additional, not additional, total, so about two more watts per meter squared of energy, okay? And then in those sort of worst case or bad case scenarios, we accumulate between 6 and 8 watts per meter squared total, or about 4 to 6 additional over what we already have watts per meter squared of excess energy. So that would produce a lot of warming, presumably. A lot of that energy is, of course, going into the oceans, as we mentioned in the last class, because oceans are really good. They have a high specific heat capacity and are very able to absorb a lot of energy, excess energy. So like 90 to 95%, again, of all the excess energy from climate change has gone into the oceans. The rest has gone into melting ice and warming the atmosphere. So this is adding on top of that, okay? An additional X amount of watts per meter squared. Okay. So these are the shared socioeconomic pathways. I'm going to take a sip of my Crystal Light. It kind of looks like wine because it's in a wine glass, but it's not wine. I wish it was Diet Dr. Pepper or Coke Zero. as you know, but it's not. Okay, so we have these shared socioeconomic pathways. We have sort of a vision of the future in 2100, what that's going to look like economically and socially. So now, how do we model what that's going to look like in terms of climate change, in terms of the warming? And the way we do that is we use a climate model. Okay, a climate model is essentially a computer program, a million plus lines of computer codes, a bunch of mathematical and physical equations that represent the Earth. So it's a bit more complicated than this, but we hit go, and all of these equations that model things like the atmosphere and how things move through the atmosphere, how clouds form, how rain happens and how it's distributed across the planet, how plants grow, how ice melts, life in the oceans, etc., etc. We run this for X amount of years, and it depends how long. Depends sort of it's model dependent on how long it actually takes in real life to run like a year's worth. But presumably, if you're running 100 years at a pretty high resolution, that's going to take a couple of weeks, days to weeks potentially of running a computer model. And at the end, we get a representation of what that climate looks like at the time specified, right? So climate models are an incredible tool that climate scientists use and have been using for many years to represent what we think the physical climate is going to look like in 2100. And the development of climate models has come a long way. So who remembers when the first paper was written about the greenhouse effect? So the first publication in the scientific literature that sort of called out the greenhouse effect and noted that carbon accumulation in the atmosphere could trap heat and warm the planet, that happened in 1896, a long time ago. So for those climate deniers who try to tell you that climate change is like a new thing, or we still don't know enough about it, they're lying. We have known at least about the greenhouse effect and potentially sort of the implications of the warming effect of carbon and carbon dioxide in the atmosphere for 125 years. So this paper, which was published in the Philosophical Magazine and Journal of Science in April of 1896, was titled "On the Influence of Carbonic Acid in the Air Upon the Temperature of the Ground" by a scientist, Svante Arrhenius. I think I'm saying that right, but if not, there's no one here to correct me. So carbonic acid in the title is just what they called carbon dioxide at the time. We now call it carbon dioxide. We know a little bit more about it. So this understanding of the greenhouse effect was our beginning of being able to represent the climate system using a model. And these models are known as radiative transfer models. And they were first developed in the 1890s. They rely on just sort of knowledge and data of the radiation, incoming and outgoing, and what's in between. Carbon dioxide, clouds, aerosols, whatever. Okay. Typically, they were done initially on sort of just a one-dimensional column. We now can represent the whole globe three-dimensionally using these very advanced radiative transfer models. And then in the 1950s, an incredible advancement was made, and that was the introduction of the computer, a miraculous tool that can do mathematical calculations extremely quickly, very fast, much faster than the human brain and pen and paper can do. So in the 1950s, specifically this paper from 1956 by Norman Phillips, The General Circulation of the Atmosphere, a Numerical Experiment, was sort of one of the first papers to model how the atmosphere moves using a computer, right? And this was a great advancement. It improved our ability to, for example, forecast the weather in addition to climate. And around this time, in 1955, Gilbert Plass wrote a very seminal paper about climate change that I believe I assigned you all to read, actually, called The Carbon Dioxide Theory of Climatic Change. And this was published for widespread public consumption. This wasn't just sort of a specialized scientific paper. There were write-ups in the New York Times, everywhere. Again, this was, 50, 60, 70 years ago, almost. Almost 65 years ago. Long time ago. And while Gilbert Plass was not right about everything, he was right about a lot. And so our understanding of climate change has been around for a long time. So in the 1960s, in these large climate models, we started to include things like nonlinear fluid dynamics, the hydrological cycle. So we have equations to represent how air and gases move. We consider the atmosphere to be a fluid, of course, and also how water circulates and cycles through the Earth's system. So combining the radiative transfer models of the greenhouse effect and nonlinear fluid dynamics and the hydrological cycle, we began to get a much better understanding of the Earth's system. In the 1970s, we started to include sea ice and land surface modeling. In the 1990s, we included things like atmospheric chemistry, and then in the 2000s, things like aerosols and vegetation, so how plants breathe and how plants grow and what that means for carbon dioxide in the atmosphere, what that means for the temperature of the atmosphere and the amount of water in the atmosphere, et cetera, et cetera, et cetera. And then in the 2010s, and more recently, we've started to include biogeochemical cycles and carbon cycling, and our models are now very advanced. They are millions and millions of lines of code. The model that I worked with when I was a graduate student and postdoc was the NOAA NCAR, National Center for Atmospheric Research climate model, and I tinkered around with fire, particulates, and aerosols in that model, and what happens to the climate if you change how many fires there are on the planet and how much emissions they put out. And so now we call these models Earth system models. They model the whole Earth system, and they're really good at sort of projecting and forecasting what we expect the climate to look like at an unspecified date in the future. So obviously we can't time travel yet, although I think we would all probably time travel to the end of this COVID nightmare. But since we can't time travel yet, we have to use models to sort of represent and forecast what we think the climate will look like under various scenarios. All right. So that said, layered on top of these socioeconomic pathways are mitigation target scenarios, which we call representative concentration pathways, RCPs. More crystal light. So representative concentration pathways are physical models which envision in the future, in 2100, a world where X amount of excess radiation has been absorbed by the Earth system. And these range from 2.6 watts per meter squared additional radiation by 2100, all the way up to 8.5 watts per meter squared of additional radiation. And I also just realized that I made this slide and forgot to delete the old figure that I had in back. So, contrary to popular opinion, I am not perfect. Anyway, So you can see that some of these, so 2.6 is like additional watts per meter squared over the baseline, would be the best case scenario of warming. 8.5, which on this graph is baseline, would be the absolute sort of worst case scenario. And so you can see that not all of the SSPs can achieve all of these RCP scenarios. So for example, SSP1 is the only scenario that can achieve the 2.6 watts per meter squared best case scenario of warming. The SSP3, 4, 3 and 5, sorry, are the only ones that can achieve, if we consider it an achievement, the worst case scenario, that 8.5 watts per meter squared. So if we just look at those RCPs, so we remove the SSPs for a moment. The SSPs are really good. They inform us about what we think the socioeconomic status of the planet is going to be in 2100. But if we just remove those for a minute and we just look at these RCP scenarios, what do the net carbon dioxide emissions look like for each of those scenarios? And I promise that this is a lot of background and I'm getting to the punchline that everyone is waiting for, which is like, what the hell is going to happen in the next 100 years with the climate? I promise it's coming. I'm just very long-winded. So here's where we are now, right? This black line. This is how much net carbon dioxide emissions we emit per year annually. These are just observations, okay? And then these lines are the various representative concentration pathway scenarios. So ideally, I mentioned, right, that we have in the climate system right now, you know what? My wonderful partner made me a whiteboard. So right now we have about 2.5 watts per meter squared of excess warming in the climate system. So the best case scenario sees us at 2.6 watts per meter squared of warming by 2100, or basically no change from where we are now. The worst case scenario sees us at about 8.5 watts per meter squared of warming by 2100. And then everything in between. We have 3.4, 4.5, 6, and even a 1.9 watts per meter squared, as you can see here, scenario has been added on post when a lot of these figures were made. So at the time, 2.6 was the best case scenario. Now 1.9 is sort of the best case scenario, which will be included in the next assessment report put out by the United Nations. And so you can see that sort of in the best case scenarios, the amount of carbon dioxide that we emit per year after about 2060 or 2070 is negative. So you're probably like, how is that possible? Well, the way it's possible is that we actually, in these scenarios, will begin removing carbon from the atmosphere. That's why these are the best case scenarios, and at least considering the track that we're currently on, highly improbable, unfortunately. The worst case scenario up here is just sort of like a disaster, honestly. And then the 6.0 and the 4.5 scenarios are kind of in between, okay? So 4.5 watts per meter squared, so an additional 4.5 watts per meter squared of warming over the 1900. These are all above about 1900 or so. So sort of at the beginning of, what some people refer to as the Industrial Revolution. I prefer not to call it a revolution because, for reasons that we can talk about on the Slack. But, God, this camera's complicated. Oh, this side's better, I think. Yeah. So the 4.5 watts per meter squared would be an additional 2 watts per meter squared of warming of energy capture above where we are now. This is kind of in line with the Paris Agreement. Okay, so the Paris Agreement, the guidelines outlined by the Paris Agreement would put us on the path to about 4.5 or about 3.4, between 3.4 and 4.5 watts per meter squared of warming. And we'll talk about what that means in terms of temperature rise in a minute. Okay, so does anyone have any questions on this? If you do, please write them down, and then let's talk about them together in the Slack. This whiteboard is amazing. I'm going to just erase this. Okay. You didn't think I was going to pull out the whiteboard, did you? Oops. So not all, again, as I mentioned, not all SSPs can achieve all RCPs. But let's talk about what this means in terms of temperature rise. This is what everybody wants to see, right? This is the punchline. So in the best case scenario, so here's where we are now. So the black line is what the climate models think the temperature has been for the last 100 years. So you're probably like, why don't we just use the actual temperature? We do. We use the actual temperature to validate and to help sort of fine-tune the models so that they're giving us an accurate representation of the Earth system. But since we're showing projections into the future, I want to show those projections with what the model thinks happened in the last 100 years. But I will say that what the model thinks happened in the last 100 years is essentially what happened. It's very, 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 very close, highly correlated. The models are good. The models are really good. So what we have seen over the last 120, 150 years of climate change is about 1.2, pull the whiteboard out. So we've seen about 1.2 degrees C of warming. Under the best case scenario, the blue line here, we would see maybe an additional half to a degree or so of warming. That's important because, so it would be 0.5 to 1.c additional of warming. That's important because if you listen to Alexandria Ocasio-Cortez, if you've read the Green New Deal, if you've heard reports by the United Nations and other scientists and bodies that look at climate change, in order to prevent what climate scientists call catastrophic climate change, we need to keep warming below about 2 degrees C of warming. So if we are at about 1.2, we have about 0.8 left. So we have 0.8 degrees C of warming remaining, and in the best case scenario, we would probably achieve that. And so we would prevent what climate scientists call catastrophic climate change. Great. In the RCP 8.5, which is the worst case scenario, we would blow past catastrophic climate change on our way to an additional 4 or so degrees of warming, bringing us between 4 and 6 degrees of warming total throughout the course of sort of all of climate change since the mid-1800s. So our simulations then, using these RCPs, range from about an additional half degree of warming or a degree of warming to about 4 or 5 or 6 degrees of warming. And then everything in between. So you can see the 4.5 scenario, for example, gets us about another 1.5 degrees or so of warming, which would put us above that 2 degree threshold, but not by much. And so I like to say while 2 degrees of catastrophic, while 2 degrees C of warming and below would be ideal, 2.1 is better than 2.2, is better than 2.3, is better than, etc., right? So we don't just throw up our hands at 2.0 and say, well, we're fucked. Guess we better do nothing. It's always better to do something than to do nothing. If we want to put that in perspective of the last 1,000 years, it's very stark. So you can see that the temperature for the last 1,000 years has been, as we talked about in class, has been incredibly consistent. In fact, for the last 10,000 years or so, the global temperature has been incredibly consistent in a very stable climate regime, which geologists and scientists have called the Holocene. So during the Holocene, during the last 10 to 11,000 years, right, that is when everything that we know about how humans exist on the planet came to be. Cities, healthcare, books, writing, art, music. Well, maybe not music. But anyway, all of that kind of happened in the last 10,000 years in a very stable climate. And you can see that climate change is already ruining that stability. We're already on the uptick. And again, these are the estimates of warming, right? The highest estimates are between 3 and 6. This should be a Celsius. So many mistakes. 3 to 6 degrees Celsius of warming, which for those of you who are familiar and can convert to Fahrenheit, is a lot more than 3 to 6. It's like 5 to 11 degrees Fahrenheit warming. That would be beyond catastrophic. That would be a world that none of us recognize in 100 years. All right, let's break it down and let's look at sort of each individual variable. Let's start with temperature. So I have shown a version of this graph in class. This is the annual temperature. Each black dot is the annual temperature anomaly. And the period chosen for normal in this graph, for 0, is the average of all the years between 1880 and 1920. So all those years averaged together is the normal starting climate, and that's 0. So if you add all these up together, you would get 0. So what this graph is showing is how far away each individual year is from that 0. And it's basically a proxy of how much the world has warmed. You can very easily go and look over and see, 1.2, that number I've been saying, that's how much the globe has warmed. So you can see rising a lot since 1970. 2019 is officially in as the second warmest year on record. And all of the top 5 warmest years on record, as you can see, have occurred in the last 5 years. Lucky us. So this graph is, I think, very abstract and difficult to understand and comprehend. And so as I drew in class, and will draw again very quickly for you right now, what this warming means, because I think it's difficult for people to conceptualize, well, 1 degree of warming means, because 1 degree seems like nothing. So what's actually happening is that the distribution of temperatures is shifting. So if I am at a given point on the planet at any given time, the climate says that there would be an average temperature. But statistics would say that there's a distribution of temperatures that could occur. So today on March 29th, I don't know, the average temperature is about 51. That's the average high, 51 degrees Fahrenheit. But it could be 30, it could be 70, it could be 80, right? So there's a distribution of temperatures. So this is what, this is what the distribution of temperatures looks like on the climate right now. With climate change, this distribution shifts. So the average goes higher, right? So the new average would be higher, but the whole distribution would shift. So now, if this used to be kind of what we considered warm weather, in this new regime, the likelihood of it being warmer just increased significantly, right? This is all more. So it's not just that the average temperature is increasing. It's that the whole distribution is shifting. And so the likelihood of extremely abnormally warm days has increased significantly because of climate change. So it's not just this abstract line up. It's actually a shift in distribution, which is allowing for more warm days. It doesn't preclude that there could still be cold days. There can still be cold days over here, right? These are cold. They still happen, but they're less likely to happen because the whole distribution has shifted to the right. So this axis here is likelihood. Should probably write that in. Sorry, I'm not used to drawing on a mobile. So likelihood on this axis. So this is obviously the most likely, and then you decrease in likelihood, but the shift in distribution means that what used to be the most likely is now less likely, and a warmer temperature is more likely. And it's way more likely that you'll have hot weather. Okay, does this make sense to everybody? Oh, I wish we were like in person so you could ask me questions, because I know that I'm explaining this not great. All right. Voila. We have actual data showing this from the New York Times. This is an article from 2017 from the New York Times showing this shift in distribution of summertime temperatures in the Northern Hemisphere. So the gray distribution here are the distribution of temperatures from 1951 to 1980. And then the colored plot here is the distribution of temperatures from 2005 to 2015. You can see that the peak has shifted to the warmer end of things, but hot weather, right, is now significantly more likely to occur. What used to be normal is now kind of on the cooler end of the distribution spectrum. So this isn't something that we just made up. This isn't just a whiteboard drawing that I made. This is evidence. This is actually supported by evidence and data that we have. I will note that the tails of the distribution, of the shift in distribution, are getting a little longer, so we can still have extreme cold. In fact, some people think that extreme cold is actually getting slightly more frequent, and that's because the variability of the temperature is increasing. But that's a conversation that you should ask me another time to explain. All right, so what's going to happen? What's going to happen in 2100? Let's compare maps of the best case scenario and the worst case scenario. So the RCP 2.6 again is the best case scenario, and the RCP 8.5 is the worst case scenario. All right, I'm just going to move my ugly face up here. So in the best case scenario, right, we see by 2100 or so, relative to the last couple decades of the 20th century, temperatures rise on average across the globe between 0 and 1.5, maybe 2 degrees of warming or so, which is in line with sort of what those XY graphs show. The worst case scenario is not cute. Worst case scenario shows warming of anywhere from 1 to 11 or 12 degrees C, and that's bad. It doesn't take me telling you that. I think these figures speak for themselves. It's not a pretty future. The RCP 8.5 is not a pretty future. Another thing that you might notice is that the warming is the highest at the North Pole and at the South Pole a bit, but the North Pole really sticks out. This is a problem. This is problematic because there's something at the North Pole that also regulates the climate, and that is sea ice. That is ice. It's cold at the North Pole. Ice and snow are abundant in the northern sort of high latitudes and over Antarctica as well. And white snow and ice reflect sunlight. They actually keep the temperature regulated. They keep it cooler than it otherwise might be. So if you get rid of all that ice, which we are doing, and I have a couple slides on the ice stuff, then you warm the temperature of the poles up significantly. And that's why you're seeing, especially in the worst case scenario here, that the North Pole warms anywhere between 7 and 11, 12 degrees C by the end of the 21st century. That's because of that feedback between the loss of very bright reflective sea ice, and that's being replaced by dark blue absorptive ocean, right? You can see it even in the sort of best case scenario. There's still a loss of sea ice that allows for the North Pole to warm significantly more than the rest of the globe. You'll also notice in both of these figures that the continents warm more than the oceans. That is supported by evidence, and that is important because people don't live in the oceans. As much as I secretly love Waterworld, that horrible movie from the 90s, is it? When I was a kid. We do not live in the water. We live on the land. And I really hope you all are laughing to my incredibly bad jokes, just like we're in class. So the continents where people live are likely to experience an exaggerated form of climate change. This is important because even if the globe warms by 2 degrees C, the continents may warm by 3 or 4 degrees C, which is where we live. So that's what will affect us more. If we break this down and we look at how this will change not just the sort of average temperature, but the temperature of the hottest days and the coldest nights, you see something that's very stark. Okay, so what I'm showing here are best case scenarios, 1.5 and 2 degrees C of warming, right? So 2 degrees C of warming is kind of that threshold for catastrophic climate change, right? So even in the 2 degrees C of warming scenario, I'm going to move this over here so you can see that, the average temperature of the hottest days of the year goes up still by 2 or 3 degrees C over the continents. This is a problem because when we think about climate change and the effect that it has on our lives and on our world and on our economic system, on our social system, right? One thing we're very concerned about is heat waves. So if the hottest days are increasing more than the actual global average increase, that essentially is a proxy for, an analogy for, we're going to have more heat waves. Okay? So that's a problem. Let's also look at the coldest nights. The coldest nights see an incredible increase, especially in the northern latitudes. So those coldest nights of the winter, right? Even in a best case scenario, are going to be 4 to 10 or more degrees C warmer than they are now. Okay? In a best case scenario. So a lot of the warming that we've seen over the last 100 years and will continue to see for the next 100 years is happening at night. Not during the day, at night. It's very insidious because it's happening at night. We don't notice it a lot. But sometimes, like especially in recent years, if you go outside, you might think, well, the day felt normal, but the night feels so much warmer than it should be. That's real. You're not just imagining that. That's real. And that's likely to continue and increase. That's a problem, especially in cold climates. Vegetation and especially, for example, I'm just thinking off the top of my head, apple trees, for example, require very cold nights in order to, again, produce fruit in the spring. Insects. A lot of insects die in the winter because it's so cold. This is important for maintaining the health of our forests and our crops. If the coldest nights, especially in the winter, are now much warmer, perhaps insects don't die, and you get an outbreak of bark beetle infestations, as we've seen in the western United States, for example, in the past few decades. That's, a lot of people think that's partly because bark beetles are not dying in the winter because the winters are getting significantly warmer, especially at night, when it should be very cold. Okay, that's temperature. Let's talk about precipitation. So here's a picture from just last year in the Midwest when we had historic, devastating floods. You may remember these. They were in the news. Awful. Totally destroyed a lot of cropland, a lot of cities, a lot of livelihoods. Unfortunately, this is something that we may see more of in the future. So just looking again at these maps, right? So we have the 2.6, I forgot to put the labels here, but this is the best case scenario and then the worst case scenario. You can see the change in the average precipitation follows a similar pattern between both the best and the worst case scenarios. In the best case scenario, changes to precipitation are on the order of 10, maybe 20%. In the worst case scenario, in the 8.5 scenario, changes to precipitation are as high as 20, 30, 40, 50% difference. So precipitation is likely to increase, for example, at the equator and in the North Pole and the South Pole. And that's denoted here by these dark blues and greens, and likely to decrease in between. So in this sort of drier, more arid, kind of deserty areas. And by as much as 20 or 30%. Okay, so that means drought. And the increase means more flooding. But we're also likely to see changes to the extreme precipitation, okay, which is a better measure of drought, actually. So again, showing just the best case scenarios here, right? Just the 2 degrees C preventing catastrophic climate change. Also, do you hear my dog walking around? He wanted to be part of this, I guess. So just in the best case, sort of avoiding catastrophic climate change, we still see an increase where we're expecting precipitation to increase. That precipitation on the most rainy days will increase by 20, 30%, meaning floods, where they're expected to be more floods, are going to be worse. Same thing goes for where it's supposed to get drier. The decrease in the driest days and the amount of precipitation in the driest days of the year is going to go down, which means that there's a higher likelihood for droughts. So where we see droughts now, we could see droughts but worse droughts. Where we see floods now, we could see floods but worse floods going forward. We'll also see worse storms. A lot of people talk about hurricanes. We're not going to see more hurricanes. We're going to see worse hurricanes. So this figure on the left here shows the model simulations of Category 4 and 5 tropical storms. Okay, so in the present day simulation, we have on average about 244 Category 4, Category 5 hurricanes, tropical storms, denoted by the red and the dark red, or the red and the brown. In the 4.5 scenario, in the middle of the road, Paris Agreement, kind of decent case scenario, by the end of the 21st century, that number bumps up to 313 Category 4 and 5 storms. But the number of total hurricanes doesn't increase by that much. It's just that the hurricanes that do exist are going to get worse in the models, in our simulations. Okay? So not more hurricanes, worse hurricanes, longer lasting hurricanes, rainier hurricanes, windier hurricanes. Okay, more damage. Additionally, here again are those figures of extreme precipitation events. So this figure in the middle shows the change in the amount of precipitation that falls on the rainiest 5 days of the year. So pick any location in the world and find its 5 rainiest days. And then how is that going to look at the end of the century in a worst case scenario? And pretty much everywhere is going to see an increase in their 5 rainiest days, an increase in the amount of rain that falls on their 5 rainiest days. For dry days, meaning more floods, right? So for dry days, the number of dry days in a row, okay, consecutive dry days, for the places that are already dry, okay, so like Northern Africa, Southern Europe, Western Asia, Australia plagued by wildfires, the Southwest United States and Mexico. Those are all likely to see in a worst case scenario an increase in the number of days where no precipitation falls. So an increase in drought probability occurring. Okay, let's talk about sea ice. Hang on a second. Okay, we're back. I did this once and the QuickTime froze and then that was a disaster. All right, we're getting close to the end. Let's talk about sea ice. So sea ice is changing. I mentioned sea ice follows an annual cycle. Sea ice is highest. The amount of sea ice is highest in about April, at the end of the winter, the long winter in the North Pole. And then it's lowest in the fall at the end of a short summer. So it usually bottoms out in September and it peaks in April or so. So now. And you can see that just historically speaking, beginning in the 1980s, the amount of ice during the course of this cycle over the year has continually decreased. So the 80s are dark blue, the 90s are light blue, the 2000s are a whitish color, and the 2010s are dark red. You can see 2020 on here falls right in that range. 2020 was a particularly cold winter in the Arctic, but it's now warmed up and significantly above normal, and this has plummeted to near record lows. This is as of, I believe, March 1st or so. And these sea ice figures are taken from a colleague of mine, Zach Labe, at UC Irvine. Great, really nice graphics. You can follow his Twitter here, zlabe. Yeah, so historically we've already seen sea ice declining, not just in the summer, but also in the winter. And of course, as you might expect, the projections are for sea ice to continue to decrease, unfortunately. So let's look at just the summertime here, over here. And you can see these are the projections for each of the scenarios compared with the observations. So this is the extent of Northern Hemisphere sea ice in September, when it's the lowest, when it's kind of at its lowest amount at the end of the summer melt season. You can see, though, unfortunately, that observations are outpacing all of the model projections. So the observations are in green, we're down here. The model is projected we might be still up here. So that's not cute. Sea ice is declining faster than our models are projecting. So there's been some fine-tuning to the models. This figure over here shows the same thing, but for February, when sea ice is at its highest amount because of the winter, or approaching its highest amount because of the winter. So what does that look like in terms of kind of a map? You can see here's the average at the end of the last century, and here's the average in the RCP 4.5. So the middle of the road scenario, sort of a Paris Agreement type scenario. You can see that even in this scenario, the Arctic is relatively ice-free by the end of the century. Of course, in the worst case scenario, the Arctic in September is completely ice-free. No sea ice in the Arctic in September, in the worst case scenario. Still some sea ice, though, in the winter. It still gets cold in the winter. It's still dark. And so there will still be sea ice in the winter, even in the worst case scenario. But no sea ice in the summer is particularly problematic because in the summer, that's when there's sun in the Arctic. And sun is absorbed by dark blue ocean water. If there's no ice in the way to reflect it, it's absorbed by dark blue ocean water, and this speeds up the effect of warming. So if we eliminate all of our Arctic sea ice, we will see an increase in the amount of warming just from the exposure of a dark blue ocean. Okay, so we've covered temperature, we've covered precipitation, we've covered sea ice. Let's talk about sea level rise and then a couple little odds and ends, and then I'll be done. I know I promised that this would be about an hour, but I'm apparently very long-winded. So sea level rise. Sea level is rising. I'm sure you have heard this in the news. I'm sure you've heard stories of sea level rise. We talked about sea level rise in class and why it's problematic for coastal communities, not just the absolute level of the ocean, but also because during bad storms, you get a storm surge, and if the sea level is rising, the storm surge is going to be even higher, and that's going to inundate areas inland that are maybe not necessarily below sea level, but will be affected by sea level rise. From a data standpoint, we are observing a sea level rise of about 3.4 millimeters per year, which in terms of inches, well, 1 inch is 25 centimeters, 25 millimeters, sorry, so 3.4 divided by 25, someone can do that math. It's about an eighth, right? So an eighth or so of an inch per year, sea level rise. So every decade, that's like over an inch. That's the rate we're on now. You can also see that it's increasing in recent years. Since 2010 or so, the rate of sea level rise is increasing. So what do we expect by the end of the century? Here is another, honestly, the video, moving where my video is like the most complicated part of this whole thing. So here's what we expect to happen in the various RCP scenarios. So mean sea level rise above where we are now in the year 2000, or where we were in the year 2000-ish, is projected to rise an additional 50 to 250 centimeters, with the median being about 1 meter of sea level rise, or just over 3 feet. So 3 feet of sea level rise is the projection, median projection, by the end of the century. Okay, so 3 feet of sea level rise. You'll see this this number in a lot of different places. It's kind of a benchmark number that's used by a lot of scientists. When we talk about sea level rise, we talk about 1 meter or 3.3 feet of sea level rise. The problem with this number is that sea level rise is something that is really slow. It's a slow process. There's inertia that's built into the system that will continue beyond the year 2100. So, yes, we might see a meter of sea level rise, or yes, we probably will see a meter of sea level rise by 2100. But even if we were to stop emitting carbon dioxide today, sea level will continue to rise beyond 2100 to 2200, 2300, 2500. And if we continue on a worst case scenario, on an 8.5 scenario, sea level rise will continue for millennia. No, not millennia, maybe centuries, depending. For centuries. Okay? So this isn't something that just ends in 2100. I mean, the same goes for temperature and precipitation and all that. But sea level rise in particular is something that's such a slow process that it continues beyond 2100. And I personally foresee sea level rise being an enormous problem that we are just not dealing with. Actually, we're not even considering what to do with sea level rise. If you're interested and want to play around with sea level rise, and what it looks like in your community, you can go to this website right here. Just Google surging seas, and you can like play around with it, and it'll show you kind of what the world will look like with sea level rise. By the end of the century, you can play with different scenarios, and it's really cool. All right, so while we're on the topic of oceans, let's talk about what's going to happen actually in the oceans. So ocean temperatures are going to warm. You have best case scenario, middle case scenario, worst case scenario. In all of the scenarios, the ocean warms. In the worst case scenario, the ocean warms significantly, a degree or more Celsius of warming in the surface ocean. It's a real problem. So why is this a problem? This is a problem because not only are oceans warming, but they're also acidifying. They're acidifying because carbon dioxide, where to put this? Carbon dioxide, when it's dissolved in water, produces H plus ions, which make water acidic. And so in the worst case scenario, here in the 8.5 scenario, the acidity of the ocean, the pH, of the ocean will decrease from where it is now, about 8.1, to perhaps below 7.8. Remember, 7 is neutral, neutral acidity. Anything above 7 is basic, like me. That's my best joke of this whole lecture. Anything less than 7 is acidic. So a decrease in the pH means an increase in acidity. And you can see that this acidity will be distributed across the oceans worldwide. It's not going to be discriminatory. It's going to be all oceans everywhere. So when you combine warmer oceans with more acidic oceans, you have the unfortunate coincidence of the loss of a lot of sea life that has carbonate shells. So probably the most iconic of these creatures that will be harmed by this is the coral and coral reefs. And that's because coral is partly comprised of a carbonate shell, and they make that carbonate shell from dissolved carbon dioxide in the ocean. So this has always been the case throughout history of the Earth, of the oceans, of carbon dioxide being in the atmosphere. This equation here basically describes the process. So you dissolve carbon dioxide in water and you get a carbonic acid. That carbonic acid breaks down, and I hope some chemists are watching this live video so that you can correct my terrible chemistry, but this breaks down into an H plus hydrogen ion and a bicarbonate ion, which further breaks down into two H plus ions and just a straight carbonate ion, CO3 2-. But this equation goes left and right. And if there are too many H plus ions, if it's too acidic, right, if it's too much on this side of the equation, then it's going to want to move back to the other side. And in order to move back to this side, it's going to need to consume some carbonate, which means that it's going to consume the carbonate from shells of dead coral. How did those coral die, or how did they bleach? They did that because the ocean got warm. So the ocean warms up, the coral are stressed, they get bleached, then their carbonate shells are consumed by this chemical process, and those coral are gone forever. And this is what's happening to all of the coral in our oceans now, and this process is probably going to accelerate going forward into the future. Let's look at some relatable changes here in the United States. Let's look at the frost-free season length. So observed increase in frost-free season length. So here in the Midwest, for example, we've seen our frost-free season, meaning the number of days in between the last frost in the spring, which we are rapidly approaching here. Typically in Chicago, the last frost is between April 10th and April 30th or so. That's the last night that it's below 32 degrees on average. The time between that and then the first frost in the fall, which is typically in October for Chicago. So here in the Midwest, we have observed that average season, that frost-free season, increased by about 9 days. And with climate change, by the middle of the century, that's what this figure is, by the middle, by 2060, we are likely to see that frost-free season increase by as much as 20 or so days. So an extra month. So where the last frost is now occurring in late April, maybe it's occurring in late March or early April, and the first frost is not occurring until November, something like that. Okay, so a shift. This is a problem because farmers grow crops depending on how long the frost-free season is. If the frost-free season is too long, you might think, oh, that's probably a good thing. No, because it's too hot now in the summer. So agriculture will shift northward. So a lengthening of the frost-free season is typically associated with a shift northward in agricultural land. Okay, looking at the number of days above 90 and the number of days below 32, if we just focus on the top plots, the bottom plots are the same thing, just the data shown in a slightly different way, not weighted. You can see that the projected change in number of days above 90 degrees by the middle of the 21st century for Chicago, for example, is an increase potentially of 20 or 30 more days above 90 degrees. So right now we have about 20 days or so a year, so we would be doubling that. And then for the number of days below 32, we would see a decrease of approximately 20 to 30 days below 32. Okay? So almost an entire month less of days below 32, and that kind of corresponds really well with the frost-free season length. Okay, this is kind of saying the same thing, so I'm actually going to skip this plot because I'm starting to lose my voice, and it's essentially the same information. It will be in the PowerPoint, which I'll post to the Google Drive. I wanted to sort of conclude this by just touching on the changes that may be occurring to the polar vortex because of climate change. So normally, you have very cold air at the North Pole and very warm air at the equator, and that gradient increases in the winter. The North Pole gets significantly colder, and the equator stays about the same. And what that does is it creates a very strong current of air between circling the Earth called the jet stream, the polar jet stream, right here. And that creates a very stable polar vortex. Okay, it keeps all that cold air north at the North Pole. As the North Pole warms because of climate change, that gradient decreases between the North Pole and the equator, which means that the strength of the jet stream decreases as well. And when the strength of the jet stream decreases, it starts to meander, and it becomes very wavy. And every now and then, one of these waves dips down into the Midwest and brings us very cold Arctic air. Okay? This happened last year in January. It was minus 23 degrees Fahrenheit in Chicago. A lot of people called it the polar vortex. It's kind of a misnomer. The polar vortex actually weakened, which allowed air that was in the polar vortex to slip southward into Chicago, probably because of climate change. This hasn't been definitively linked, but this is one hypothesis that is gaining some traction. Okay, finally, everything we do with climate change doesn't end in the year 2100. Okay, even though I've shown you a lot of plots that take this out through 2100, they don't end in the year 2100. They continue for a long time. So here are simulations of one model where they basically ran the worst case scenarios past 2100 to 22 and 23 and 24, all the way to the year 3000. And you can see that even though in all of the scenarios, even in the worst case scenario, eventually carbon dioxide emissions go down to zero, presumably because we run out of fossil fuels eventually. So in the worst case scenario, fossil fuel emissions, carbon dioxide emissions, go to zero by 2300. In the best case scenario, they go to zero by 2050 or so, right? That doesn't mean that the amount of carbon dioxide in the atmosphere goes to zero. In fact, the amount of carbon dioxide in the atmosphere stays elevated forever. Not forever, but in terms of the human sort of scale, forever, as far as we're concerned. For 1,000 years, carbon dioxide concentrations in the atmosphere would be significantly elevated. This is because the globe would shift to a new equilibrium. The globe would just accept, the planet would just accept, this is the way it's going to be. I'm going to have to reorient the way I do everything. And that carbon dioxide would stay in the atmosphere for a very, very, very long time, 1,000, 10,000 plus years. And as you can see, the surface temperature would go up and stay up. So everything we do now, every decision that we make now is going to last for a really, 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 really long time, representing a potential shift in the entire climate of the Earth's and a total shift in the Earth system. This would precipitate a mass extinction, which we talked about in class on like the first couple class lectures. This would fundamentally change the way that not only human beings, but all species exist on the planet for millennia. And for those who are interested in sort of reading about some of the more specific things that might happen with each degree of warming, I recommend this book, 6 Degrees, Our Future on a Hotter Planet by Mark Linus. It's good reading, it's accessible, it's a great book. So I want to finish with this kind of complicated figure, which shows the way in which each of these sort of components of the Earth system and components of the way in which human beings interact with our Earth system would change for each of these degrees of warming. Okay, kind of based on that 6 Degrees book. So just looking at, for example, food, okay, the middle column here, with each degree of temperature change, right? Different things happen. You have cereal productivity decreasing at low latitudes, and then eventually decreasing for all cereal growth. Cereals are like grains and like corn and wheat and rice and sorghum. But at the same time, for about 2 degrees of warming, cereal productivity would increase in the mid and high latitudes. That's what I was saying about that shift northward. In terms of ecosystems, right, at 2 degrees of warming, we risk up to 30% of species extinction. By 4 or 5 degrees of warming, in the worst case scenario, significant extinctions around the globe. Corals are being bleached and dying. There are shifts in where species can live, where wildfires can occur. The coastlines are being affected. So I'll leave this up for a second for you to kind of just look over. But I want to just talk about this last column here. I think it really pertains to kind of what we're going through now. So while the whole coronavirus pandemic is not actually attributed directly to climate change, one thing that we do expect to occur from climate change and the shift in temperatures and ecosystems and all of these things is a change in the distribution of disease vectors. Okay, we've seen cases of malaria at latitudes where we didn't think we would before. For every inch of ice that melts, tons of viruses that were trapped in that ice or in that permafrost thousands and thousands, maybe millions of years ago, are now being released into the atmosphere. And these are viruses that we have never seen before as humans, and most species have never seen before. Viruses and bacteria and other things. And at 3, 4, 5 degrees C of warming, we will see a substantial burden on health services around the globe. Okay? This is increasingly a problem for human health. It's not just about sea level rise. It's not just about heat waves. It's about everything. It's about the way in which human beings and all species exist, live, interact on our planet. Okay? So what we do today is really, really critically important for the future that we want to have. Okay? Do we want a future that works for everyone, that is equitable, that prevents climate change? Or do we want to stick the globe and stick all of the species on the planet with irreversible climate change? Okay? So that is the lecture for today. I hope that this was helpful to a lot of people. And